Hi everyone, this is Kruti Jai Bancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Analog and Digital Communication System. From this video, you will learn about medium power AM modulator and high level collector modulator. In the last video, we learned about the low level modulation and the high level modulation. As we know that the low level modulation in that generation can be takes place at the low power level, and the generated AM signal is then amplified using the chain of the linear amplifiers such as the class A, B or AB amplifiers. Similarly, the high level modulation, the generation of the AM modulation that takes place at the high power level, and the carrier and the modulating signals both are amplified first, and then the adequate power level that can be added, and the modulation that takes place in the last IRF amplifier stage of the transmitter. Again, here the highly efficient class C amplifiers that can be used for the high level modulation. Hence, the efficiency of the high level modulator that is higher than the case than compared to the low level modulation. So now in this video we will learn about the medium power AM modulator. Now the medium power AM modulator, the circuit is shown in a figure over here, that we can see that here using the transistor the circuit that can be made, and modulation that takes place at the collector of this transistor, and this will be act as a output stage of the transmitter. It is the high level modulator and operates as the class C amplifier. So that is why the efficiency of this kind of the amplifier, it is 80% or up to the 80% we can say, and it is comparatively higher than the class A amplifier. Here we are applying the carrier that is at the base of the transistor. Here it is the modulating signal that we are applying onto the collector of the transistor. Here this circuit is known as the collector modulator because the modulating signal that we are applying onto the collector, and that is in series with the DC supply VCC. It is having the efficiency that is again the higher. Again the RFC that is used over here. This RFC is the radio frequency choke, which can act as a short circuit for the DC, for the DC, and it open circuit for at the high frequency. So here the job of this RFC, that is to isolate the DC supply from the carrier and the sideband, and allow the DC and the low frequency modulating signals pass through it. So this way the medium power AM modulator that works. Here this is the multiplier which will multiply the carrier signal and the modulating signal and the modulation that takes place. So it is the medium power AM modulator. So the circuit diagram of medium power AM modulator using a transistor, the modulation that takes place at the collector. This stage acts as an output stage of a transmitter. It is a high level modulator and operates as the class C amplifier. Efficiency up to 80%. Carrier is applied at the base while the modulating signal is in series with the DC supply VCC to the collector. The circuit is called the collector modulator because the modulating signal is applied directly to the collector. RFC is a radio frequency choke. It acts as a short circuit for DC and open circuit at high frequency because the inductive reactance XL is proportional to the frequency. What is the job of the RFC? It is to isolate DC power supply from the carrier and sideband but allow the DC and low frequency modulating signal passing through it as it is. Here these are the waveform which we will get. It is the collector waveforms without the modulating signal. As we have seen in the diagram that if the modulating signal which is not appeared, it will be only act as an amplifier. So you can see over here these are the collector waveform, okay, at the without the modulating signal. This is the collector current IC and it is the output that is at the VCC, okay, it is equal to the VCC, okay, these voltages. So this way we can have the output across the collector. This is the collector waveforms with the modulating signal. So you have applied the carrier onto the base of the transistor and we have applied the modulating the signal onto the collector of the transistor. So this is the modulating signal. Now the carrier will come through the base, so it is the carrier. Now here you can see that as the amplitude of this modulating signal that changes, okay, this collector current, okay, that is also changing, and according to that we can have the collector waveforms with the modulating signal. So this is the waveform of the medium power transistor modulator. So now we will learn about the next, that is the high level collector modulator. Now behind the high level collector modulator there is a principle of the tuned circuit. Now here you can see the diagram, it is of the tuned circuit. So here this property that states that whenever we are applying the current pulses to this tuned circuit, now this tuned circuit will generate this kind of the damped voltage oscillations at the output. Now these amplitude of these oscillations that is proportional to the size of the current pulse. If the size of the current pulse that is large, then these amplitude variations that is again very large. Again this decay rate that you can see, that decay rate that is againly proportional to the time constant of this, and this particular effect which is known as the flywheel effect in the tuned circuit. So this is the principle of the tuned circuit. So while the high level collector modulator is designed, mainly the function that we can understand by understanding the principle of a tuned circuit, okay. So it is the explanation about the property of a tuned circuit, that we apply a current pulse to the tuned circuit, it generates the damped voltage generation at the output. The amplitude of the oscillations is proportional to the size of the current pulse, and decay rate is proportional to the time constant, and it is referred to as a flywheel effect in a tuned circuit. Now the high level collector modulator circuit that you can see in the diagram. Now this high level collector modulator circuit, while you will draw the transmitter block diagram, this will be the last block of the transmitter circuitry, and it is the high power RF amplifier, high power class C amplifier we can say. So now here you can see in the diagram that it is the tuned circuit. Okay, so the explanation we have seen. Now what is the applied to the tuned circuit? One is the carrier signal, another one is the modulating signal. What should change? As always I said, the information should not change, but according to information these values should vary. So over here according to that this will vary and produces the output voltage. So now here you can see that the Q1, it's a final class C RF amplifier. It is the coupling capacitor C1. Okay, so this is the coupling capacitor, and here the resistance R1 you can see that. So now this Q1 transistor that receives the RF carrier signal at its base. Now whenever it will get the RF signal, this transistor will conduct. Now this transistor will conduct only for the positive half cycles, because it is biased to operate the class C amplifier. So now thus the collector current of the Q1, okay, that forms the current pulses, and that current pulses that are applied to this tuned circuit. So now again you have seen that tuned circuit, current pulses, that's the input. So according to the width of the current pulses, what happen? Whatever the input that is providing from here, okay, so the amplitude of that modulating signal, okay, that can be changed. So now the high power audio amplifier, now this tuned circuit will get the current pulses. Okay, so now these high power audio amplifier circuits are that amplifies the modulating signal. It's a high level collector. So before applying for the modulation, the signal that is amplified. So modulating signal, first it is amplified, and after amplification it go for the process of the modulation. So these high power audio amplifier that amplifies the modulating signal and to a high power level, and then from the secondary winding of the transformer T1, okay, and this T1, the secondary winding, is also connected with the plus VCC. So whatever the high power level signal is there, okay, in that the value of this VCC that can be added, okay, or subtracted, and it produces the output over here. So this way we are having the having the output, that is the amplitude modulated output at the end of this circuit. So we can say that the amplitude of the collector current pulses that can vary in accordance with the modulating signal. Okay, and as well as we can say that the AM wave that is produced by the tuned circuit. So here the tuned circuit that plays a big role for getting the modulation. So we can also say that the 100% modulation that is not possible using this circuit. Why? Because whatever the value of the modulating signal EM, that is equal to the VCC. So when the modulating signal that goes negative, okay, modulating signal that goes negative, it subtract from the VCC, and that way at the negative peak the subtraction is 0, and the 0 voltage is applied to the transistor Q1, and which produces the 0 output. So a high level collector modulator is shown in the figure. It shows the output stage of a transmitter. It is a high power RF class C amplifier. It conducts only a portion of the positive half cycle of the carrier signal applied at the base of the Q1. Transistor Q1 receives the RF carrier signal at its base, the transistor will conduct only for a portion of the positive half cycles of the carrier signal, and because it has been biased to operate as a class C amplifier. Collector current Q1 is in the form of the current pulses. Secondary winding of the modulating transformer T1 is connected in series with the DC supply voltage VCC. So the modulating voltage will add or subtract from the VCC, and the amplitude of the collector current pulses will vary in accordance with the modulating signals. This is given to the tuned circuit, and tuned circuit will produce the AM wave. So this is the diagram of the collector supply voltage. It is what the VC is equal to VCC plus EM sin omega nt. So this is what my modulating signal curve. Okay, this is the current pulses through the tuned circuit, and output of the tuned circuit for both the cycle. Okay, it is the amplitude modulated wave. The advantage of the high level modulator is better linearity, higher efficiency, higher output power per transistor. Disadvantage is impossible to obtain 100% modulation, and it requires the higher modulating signal. So this way we can say that the higher modulation, higher level modulation, that it works, and it produces the output for us. So next time we will learn about the few modulators technique. So thank you very much everyone.